Okay, so video 2, modelling motion, and we're going to look at some implications of Newton's 3 laws of motion. In other words, we're going to unpack them and finish the video with a couple of examples. Please note the context of this, we're looking at constant forces. Variable forces will come later on. So we got our 3 laws from a previous video. So law 1, body continues to stay at rest or in a uniform motion if it's not operated on by an external force. If it is, that all changes. F equals ma is the second law, or in other words, the force is proportional to the rate of change momentum. And the third one is action and reaction. For every action, there's an equal and opposite reaction. Okay, and that one's got a misconception associated with it, which we'll talk about. And because we're talking about constant acceleration, constant forces, these are never too far away. These are from a previous unit we've done, so make sure that you recall them when you need to for constant acceleration or constant force. V is final velocity, U is initial velocity, A is acceleration, T is time, S is distance. Okay, and V equals U plus AT, S equals UT plus a half AT squared, V squared equals U squared plus 2AS, and not very often we've got S as a half U plus V times T. To save time in this video, I have pre-scrawled some notes, and I'll allude to them as we go. So implications of Newton's first. So in order to start an object moving or to stop it, we require a force. A force is needed, and once something's moving, provided there's no other external forces, it will go in one direction at a certain velocity. Okay, so for straight line motion, constant velocity is achievable without any external forces acting on it. Okay, so once we have that would be a system in balance. Once we have something out of balance, so the resultant vector is no longer equal to 0, some other external forces come into the picture, the velocity changes, and that velocity might have been 0, now it's moving, or its velocity is not 0 and it's moving at a different magnitude, or a different direction, or both. So if the resultant of all the force vectors are 0, we have a balanced situation, and that could mean it stays at rest or it has uniform straight line motion. So it's a matter of balance of forces. So Newton's second law says the force is proportional to the rate of change of momentum, and we have that there in symbolic form. Rate of change of momentum is d derivative with respect to t. So we can go from a proportionality statement to an equation by using a constant of proportionality, which I've chosen to use k. K is a constant proportionality, and we have F equals k times the derivative of p with regard to t, and we can replace p with mv, and we can move that constant to the front, constant m with constant mass we're assuming, and dv dt can be written as a, so we have kma. So what we do is choose the Newton as our unit of force, and that means we can make k equal 1. So if we have 1 Newton, the rate of change momentum is 1 kilogram meters per second per second. Okay, so that's what a Newton provides us if we use that unit. Okay, so now Newton's third law, equal and opposite. Okay, so equal and opposite external forces, okay, have to act on different objects for it to be a pair, a Newton's pair of equal and opposite forces. Okay, so they have pairs, but we have to consider them provided and acting on different objects. And if you remember that, you'll probably avoid the misconception around this. Okay, so example here, and do you like my delightful bad drawing? So that is a swimming pool, alright, so there's the water under there. Don't know what that brown scummy surface is on the top, we won't talk about that, but there's the water. Now you know if that's a pool wall there and you want to go this way to the left of the screen, you need to push with your foot against the pool wall, and it will push you back at the same with the same number of newtons in the opposite direction. Okay, so that is equal and opposite on different objects. We have one opposite the other as far as the forces go, and the wall is one object and your foot is the other. If we have someone surging out of a building and going through, do you like my fire escape door? Okay, palming open the door with their hand, right, bang, right, and the door flies open. Okay, so the door accelerates and the hand decelerates. We have two objects. Okay, so that's a pair. All right, so a car getting pulled out of a bog. We have the car puts force on the rope puts the force back on the car if one car's towing another. Okay, the cases of not pairs. So if we have an object, a point mass P, with a cable with tension T and a weight, because weight is mass times G, and we have a weight of mg, those two there aren't pairs. They may or may not be equal and opposite, but they're not pairs in this particular case. Okay, we'll have a look at another example and hopefully that'll answer why. Well, here's another one. We have a book, a purple book here, which now is getting a blue coat, sitting on a table, and that table is on planet Earth. Okay, and basically that's what this big curve is there. Okay, basically if you look at the purple there, so we have mg coming down, this is the weight of the book that's sitting on a table, it's sitting on planet Earth. Alright, and that will provide what's called a normal. Now a normal is the pushback, the pushback from the table, or the reaction in other words. Now those, just like here, those are not pairs, N and mg, even though they are equal and opposite, they're not pairs because they're both acting on the same object, just like this situation here. If you have these two forces acting on one object, there's got to be two objects. They've got to be different objects. So what's the story? Because it is true that the vector n is equal and opposite to mg, but it's not a pair for Newton's third. Now this normal's got a little TB written there, and that's referring to the normal of the table on the book. So it acts from the table on the book. Down here in green we have an mg going up. Now what that does is, because of the gravitational effect of all things that have mass, see, all things that have mass have a gravitational force associated with them, and because the Earth has mass, it provides mg there on the book, but there is an equal and opposite one. So the book's gravitational force is acting on the Earth, and that's what that one is there. They're equal and opposite, so those two are equal and opposite. We need to counter this purple normal of the table on the book. There's another one here. We can see a normal of the book on the table. So the reaction of the book on the table, and those two are pairs. So that and that are pairs. Alright, the n's and the mg's are pairs. However, it is still true that the normal, the reaction of the table on the book, is still the same as the weight of the book, the force due to gravity. That's the main thing you need to know, but just a misconception. Hopefully it's not crucial for this course, but hopefully that helped a little bit there. The main thing is that you use the fact that even though they're not a pair for the third law, they're still equal and opposite. N is equal and opposite to mg. Let's look at a couple of examples to finish video off now. Example 1, 60 kilo student stands in a lift. Calculate the reaction, which that's the N. Okay, calculate the reaction of the lift floor on the student if the lift is firstly accelerating upwards at 2 meters per second, then the opposite down 2, and then moving for constant velocity. So that's when acceleration is 0. Okay, so what you do first here for part A is to create a free body diagram. You can see there where my cursor is, and we've got the object and the person in the lift. There's the object, and we have the weight is 60g, and there's a normal or reaction of the floor on the feet of the person and acceleration going up. So I've declared that positive is up. In fact, I've declared these as your positive directions. Okay, it's up to you what you do. You can go the other way in I and the other one in J if you like, but things will come out negative. That's fine, it'll still work. So vertically we're talking J, so you start with Newton's second and then say I'm going to work vertically. If you want to, once you've said that in terms of J, you can then drop the vector notation, relax that. Okay, and see we've got n minus 60g is your vertical forces, and mass is 60 and acceleration is positive 2. So we have n minus 60g equals 60 times 2, rearranging we get 120 plus 60g, or n equals 708 if you assume g equals 9.8 meters per second squared. That's the exact answer, but if you want a numerical answer, you may assume g is 9.8. Okay, so we get approximately 708 newtons, this reaction of the lift floor on the student's feet. I like saying feet. Okay, so the second one is when it's going the opposite direction, so the acceleration is going down, okay, at 2. So that I'm going to keep, you could make down positive if you want and change your model, but I'm going to keep the same model, and I'm just saying that A is negative 2. Okay, so we have the same thing, except for on the right hand side is 60 times negative 2, and rearrange in the same way and using the same assumption for G, 468 newtons. So that would make sense, wouldn't it? A less of a reaction. You've probably felt that in an elevator yourself. Okay, A is 0, so we have on the right hand side 60 times 0 because A is 0, so n minus 60g equals 0, and rearranging and using the approximation for G, 588 newtons. Lucky last now, second example, an object of mass 5 is at rest, which is important. At rest, okay, so it's at rest. It's got a velocity of 0. On a rough horizontal plane is pushed by a horizontal force of 20 newtons for a total of 5 seconds. Now the frictional force is a force on the object when it is moving is 16 newtons, okay. I've got to do two things. How far does the object travel in the first 5 seconds, and how much further will it go once you remove that force? Now, friction force, which I've talked about there, one formula associated with it is mu times n, so it is related to the normal reaction, which is related to the mass of the object, okay, if you trace that back. And mu is what's called a coefficient of friction. That's not important for this question, but it varies depending on what sort of surface, and you know intuitively that a rough surface will provide more friction, don't you? So mu times n, and it'll go up to some maximum amount. That's not strictly urgently important for this video. What we do need to do that is important is declare positive direction. I've gone for I and J like that. Draw a free body force diagram. There's our object there. Okay, so we have 5g weight, we have the normal reaction there, and that 20 Newton force they talked about, and then the friction will oppose that. Now in the I direction, which is the significant part of this, okay, because that object is, we're assuming it's not going to float through the air, and it's there to stay on the ground, but what's happening horizontally is significant. So we start with Newton's second, and in the I direction, based on how we've described positive, we have 20 minus 16i equals 5a subbing in there. Now what's really important is the magnitude of the acceleration for this question, okay? So you basically rearrange, and then you'll get 0.8 meters per second squared, okay? is the magnitude of that acceleration vector. Now we had to find how far, so we need to find s. So we've got a, and we've got information about u, so we can use s equals ut plus a half at squared. Now basically we had something that was at rest, but it has then a 20 Newton force added to it. It will provide 16 newtons of force opposing it. We will still have a net acceleration to the right. Okay, and we found that that was 0.8. So how far will it go? So ut, u being 0, means u times t is 0, and we have a half at squared, which is a half times 0.8 times 5 squared, or 25, and that comes out as 10 meters. So that's the answer to part A. It will go 10 meters in 5 seconds. Now, helping us for part B, I've just done a preliminary calculation. Velocity is acceleration times time when we have a constant acceleration situation. We know that's 0.8 times the 5 seconds. So after 5 seconds, that will have accelerated to 4 meters per second, and we need that for part B. Just remember, part B says how much further will it travel once you remove that force. Okay, so basically modifying our free body force diagram, we no longer have the 20 pulling it to the right. All the others are the same until it stops. Now this force 16 doesn't keep going. Once the velocity is 0, that friction force stops. It's dependent on something that's moved. Okay, so once it's stopped, it won't make it go back the other way. So when we do simple harmonic motion a little bit later on, or things to do with springs, Hooke's law and so on, we can find that sometimes a thing can start to go back in the opposite direction, but not this one. That's not how friction rolls. F equals ma. We're looking at, once again, in the I direction. We have negative 16 equals 5a, and we can rearrange, and the acceleration is negative 16.5 meters per second squared. And we want to know how far that will go. Now, so we have a v. The final velocity is 0, as we know, and the 4 meters per second is the initial velocity, so 4 squared is 16. 2 times a, which was there, is 2 times negative 16 on 5 times s, and to rearrange, you'll find that we get 2.5 meters until it stops, just like this video is stopping now.